we are going to learn another extremely important definition called a reference angle. And it's right here. You can highlight the whole definition. I'm going to get you to above acute. Add the word positive. Because it is a positive acute angle that the terminal arm makes with the, and sometimes I add the word nearest x-axis, but the word acute kind of makes you go to the nearest x-axis. But a reference angle always is an angle between your terminal arm and the nearest x-axis. So for example, if this angle is 35 degrees, the reference angle would be this angle back to the nearest x-axis. Notation-wise, we often use theta for angles, and for reference angles, we put a little r underneath. Now, this isn't supposed to be rocket scientist or anything like really, really complicated. So, let's see if you can figure this out. If this angle is 35 degrees, and then you decided to go back to the x-axis and write the positive angle that that's equal to, what would you get?
35 degrees.
35 degrees. Crazy, right? So what they've done here is they've drawn a whole bunch of reference angles of 35 degrees. All of these are 35 degrees. What's the actual angle in standard position? Don't look at your notes because they have the answer there. Think, how would you figure out what this is? What math would you have to do?
180 minus 35.
Does it make sense that if halfway around is 180, that's too much? That you could go 180 and then minus their 35, and that would give you 145. Similarly, sometimes you're going to get, like, oh, the angle in standard position is 145. We already know the answer, but how would you mathematically, and what would you do to figure that out? Does it make sense that you could go, well, the whole thing's 180. If I subtract the 145, I would be left with the 35 degrees that's left. So one of the things you're going to be asked to do over and over again is find reference angles. Or if you have a reference angle, find an actual angle. If this is 35, what do you think the standard position angle would be? Again, halfway around, 180, plus an extra 35, so it makes sense that you get 250. And what number would you use your math here?
360 minus 35?
360 all the way around, minus the 35. That will give you 325 degrees. Okay. Something else important for angles. When we draw our x and our y axes, that splits our grid into 4 quadrants. Mathematicians have numbered these quadrants, surprisingly, from 1 to 4. Ooh. Very, very intelligent of it. Which one do you think is quadrant 1?
Positive x, positive y, top right one.
Bottom left.
It is the top right.
You were close.
That's quadrant 1. Quadrant 2?
Top left.
It's either top left or bottom right.
Bottom left.
Yeah, there we go.
Top left.
It is top left because if you think about an angle in standard position, this is angles in quadrant 1 are positive, right?
Yeah.
And then the next angles, if you kept going in the if you attempted to speak English and your angles kept going in standard position, this would be quadrant 2. And then if they kept going, does it make sense then this is quadrant 3, and this is quadrant 4. Oh, Roman numerals. I give my other class a Roman numeral challenge. Do you guys want to take part in the Roman numeral challenge?
That's how aggressive the challenge is.
The class record was 7 seconds.
Ooh.
We actually had a competition, so we could have 2 people square off and compete. Any takers?
I only know the.
You only have to know up to 10.
Oh, well then I can.
You can, okay, Nico's one. Who wants to challenge? Nico versus Sean.
Oh,
Okay.
Sean's gonna
This is maybe I should pause the video. I think I have a very long. So, what we're going to do is we're going to start here in quadrant 1, and we have all of these have the same reference angle of 35 degrees. So we're going to just do a check and take out our calculators and figure out what sine of 35 degrees is to 3 decimal places, cos of 35 degrees to 3 decimal places, and tan of 35 degrees to 3 decimal places. Put that in a box. We need our calculators. Make sure your calculator is in degrees. Sine 35, 0.574. 0.574. Cos of 45, 0.707. And tan of 45. Whoa, I screwed up. It should be 35. I was like, where did that come from? So let's do that again. Cos of 35 should have been 0.819. And then tan of 35. 0.70. Oh, that's pretty. 3 decimal places, and they're all zeros. Okay. So first of all, just a little review of trigonometry from grade 10. What the heck does that mean? It's really important from grade 10 that you understand what that means. And usually that's something that's we like, right? If I said very important. If I tell you tan of 35 is 0.700, what does it actually mean? Okay. Well, the whole reason your calculator has these answers built in is a long time ago. They created tables of these numbers, and they found out that if you drew a perfect angle, and in this case we're talking about 35 degrees. If you drew a perfect angle of 35 degrees and made a right angle triangle, you could take a ruler and measure the sides. And the more accurate you measure, the better results you have. So I'm going to start off by not measuring too accurately, but I measured this side and it happened to be 7 centimeters. And then I measured this side and it happened to be 10 centimeters. And because I have a right angle triangle, I could do a squared plus b squared equals c squared and find out that this side is the square root of 149. Now, no matter how big or how small I drew the triangle, something happened. So I drew another triangle. I drew it a little bit smaller, 35 degrees. Wow, here we go. Still ugly looking 35 degrees. I measured this side. This time I'm like, oh, it was 3 centimeters. And I measured the other side, and it wasn't very nice. But I was like, okay, 4 point. I was really accurate, and I got a couple decimal places. I got 4.29. And I could do a squared plus b squared equals c squared, but I'm not going to right now. Because I think this is enough to show you the idea of trigonometry. The idea of trigonometry is if you have a certain angle, in this case 35 degrees, if you took the opposite side divided by the adjacent side, I go to my calculator, and I do 7 divided by 10, what do I get? 0.7, which is really, really close. I scroll up here a little bit. 0.700. Because that's what your tangent tells you. That every time you take the opposite over the adjacent, you should should always get 0.7. What about my second one, when I measured my second one? Let's see how close it was. 3 divided by 4.29. Oh, it was really close. 0.69999. Really close to 7. Why is it not perfect? Because I probably didn't measure to enough accuracy. The more decimal places I would have measured to, the closer and closer it would have made to the perfect 0.700207538. Okay? Check this out. If I do 10 divided by the square root of 149, look how close 0.819 that is to 0.819. And if I would do 7 divided by the square root of 149, 0.573. It's supposed to be 0.574. Again, my measurements might have been a little bit off. So your calculator has all of the values for every single angle built in. Prior to calculators, at the very beginning stages, people noticed this pattern. They're like, this is so cool. No matter what size of triangle I have, that ratio stays the same. And so if I know that ratio, I can figure out all sorts of mathematics with that size of triangle. That's really helpful. So what they used to do is they used to publish books. Here's a book. I have one. And in these books, the authors would say, I have taken the time to find all these numbers for you, because this is before calculators. So if you wanted to find tan of 70, you'd have to just have to turn to the right chapter and find all the numbers. This book, which is over 570 pages long, it's a really easy read. Oh, this is when things get interesting. It's just numbers. So that you would just have to find the number you needed for your calculation, take it from the book, put it into and do the math. Now we have calculators to do that, so these books are no longer published. But this one, Baron von Vega, like, this book was popular because this is the first time he went to 7 places. Previous book only went to 6 places. And I know you all know who, the superstar Vega was. I have a signed copy. I don't know how old this book is, but it's pretty cool that it's signed by the author. Right? But like here, this is building on stuff that was done by someone in the year 1705. So these tables, these numbers, used to come in books. Now they're in calculators, super nice. That's the power of trigonometry. And what we're going to look at right now is what happens when we do angles that are bigger than 90 degrees. Because first of all, can you draw a right angle triangle with, let's say, take the 145 degree? Let's just make one. Why not? Why is that bad? Why is that not possible? They're already bigger. Well, why? I'll just make this one negative.
Exactly.
They're perfect, right? Is that a realistic triangle?
Uh-huh.
No. You can't have a negative. Like, that doesn't make much sense. So we don't have right angle triangles that are bigger than 90 degrees. But what I'm going to do is I'm going to look at quadrant 2. I'm going to go to my calculator, and I'm going to see if I did 145 degrees for sine, cos, and tan, what do I get? What walks around quadrant 2? Take out your calculators. Type these in. Tell me what you get. And then tell me if you see anything fascinating or interesting as a result. Someone yell out once they got the sign one to 3 decimal places?
0.574.
What? Okay.
Negative 0.819 and negative 0.700.
That's a little messed up, eh? Okay. a little pattern. If you don't recognize the pattern yet, keep looking. You'll see something, hopefully. Now we're gonna switch colors. We're gonna go quadrant 3. Now I'm not gonna let you use your calculator.
Oh, no.
I'm so ready.
Sine of 215 degrees. So it's the same reference angle. This is why reference angles are so powerful. Tan of 215 degrees. Okay? To 3 decimal places. You might get this wrong, it's okay. But you might be very close. For sine, take a guess.
-2.
I'm not asking you.
Oh, I
asking
thought
you.
that was a class thing.
Oh, I pointed to Nicholas.
Is it 1.24?
No, it's not.
It was really guess.
Based on the patterns you are noticing, you still might get this wrong. But what do you think?
Is it 0.574?
So close, but not quite right. Anybody else want to try a guess?
Is it -0.574?
Yes, this one's negative 0.574.
How'd you get
See,
that?
that's what I was gonna say before you went.
What about the cos? It is negative. Okay, you got that one right. What about the tan?
Positive.
Tan's, yeah, it is positive.
Boom.
Okay, let's do one more quadrant 4. This time the angle is 325 degrees. Now, can you see a pattern to figure out the negatives and the positives? I think in quadrant 3 you definitely would have been guessing. But I wonder if you can figure out the pattern in quadrant 4. I need a volunteer not to answer. Okay, Nico, thanks. So now anybody else can answer. Nico was the one person who volunteered not to answer.
Thanks for everyone else, I guess.
Are they all negative, all positive? What do you think is going to happen here?
Negative, positive, negative.
Negative, correct. Positive, correct. Negative, correct. And so, weird things happen. If the reference angles are the same, then you can figure out that the decimal places will be the same. But sometimes they're positive and sometimes they're negative. And so to help you remember which ones are positive and which ones are negative, we have what is called the CAST rule. And this is what the CAST rule looks like. It is the letters C, A, S, and T, which spells the word cast. They could have called it the axe rule, or the second rule, or the astic, but I guess they went with cast. I kind of like astic. Sact rule. Could be. Stika. Yes. So they decided on cast. Now, what do you think the S stands for in the cast rule? Something, possibly to do with trade. The S?
Or no, the C.
Oh, yeah, okay, you went with the C. I asked what the S stands for. So
Oh,
you could take a trip.
I think that would be sign.
You're
possibly.
right. So the S stands for sign. And why do you think they put an S there in quadrant 2?
Because sign is neg. Nope. Sign's positive.
Sign is positive. So, okay. What do you think the T stands for?
Tan.
Tangent. Right. Okay. And why do you think they put a T in quadrant 3?
Because cosine is negative.
No.
Because sine's negative?
You guys are on fire today. Because tangent is the only one that's positive. And then, does that fit here for cosine?
No, Clementine fits better.
All right. And then the A. What do you think the A actually stands for?
All.
Actually.
I was thinking Astica.
That makes
So the
sense.
cast rule is a rule for telling us where things are positive. All of them are positive in quadrant 1. But if you get to quadrant 2 and you had a cosine, you would know it's negative because your cast rule has an S telling you only sine is positive. And now you can do some very interesting math without your calculator. For example, I could ask you to find and tell me what is, we'll do tangent. What is tangent of 135 degrees? No calculators are allowed. And this will be a question you'll have on your quizzes and tests without a calculator. Good. You're going to need your reference angle. So first of all, what is the reference angle? 45 degrees. Because 135 degrees is here, so you have to do 180 minus the 35 degrees to get a reference angle of 45 degrees. Do you know tan of 45 degrees? It's our special triangle. What was tan of 45 degrees on that special triangle? It was 1/1, which is 1, but this is in which quadrant? We're looking in quadrant 2. According to my cast rule, I have an S. What does that tell me about tangent? It's negative. I'll give you another one to figure out. What is sine of 330 degrees? You have to figure out your reference angle. 30 degrees is your reference angle. Is that one of our special angles in the special triangle? Yes, it was. What was opposite over hypotenuse on that special triangle? 1/2. And now we're looking in quadrant 4. Should it be positive or should it be negative? Negative. You are now able to do all of those without your calculator. You can find the reference angle, and the reference angle is one that you know from your special triangle. Then you can figure out. It's 2 special triangles. We learned 45 degrees and 30, 60, 90 degrees.
This is probably right in the engineering.
Okay, we'll do one more. What is cos of 315 degrees? What's your reference angle?
Oh, 45.
45 degrees is our reference angle from our 45-degree triangle. What was cos of 45? It was the square root of 2/2. Should this one be positive or negative? So we're going to be figuring out stuff with reference angles. And the powerful thing about reference angles is sine, cos, and tan. The numbers stay the same. Only thing that changes is the positives and negatives, which you can remember with the cast rule. Or if you like, you can change the letters. Just don't change the order. Because they have to be all in quadrant 1, sine in quadrant 2, tangent quadrant 3, cosine quadrant 4. And the reason that happens is actually based on SOHCAHTOA. If I erase things that we have here. And in quadrant 1, if I made a right angle triangle with that 35 degrees, I'd have an opposite side, an adjacent side, and a hypotenuse. In quadrant 2, if I went back to the nearest x-axis and used my reference angle, can you see that that's the identical triangle, just flipped? And in quadrant 3, identical triangle. If I go back to the nearest x-axis, and quadrant 4, identical triangle. But the interesting thing is, in quadrant 2, if we think about numbers and you went left, does it make sense that your x-coordinate would be negative? Your y-coordinate would be positive? And we'll always talk about hypotenuses because they're a squared plus b squared equals c squared, they would be positive. So if sine is opposite over hypotenuse, you have a positive number divided by a positive number, sign stays positive. But cos, which is the adjacent, you have a negative x over a positive hypotenuse, is negative. And tangent, which is opposite over adjacent, is negative. Look at quadrant 3. Do you see why tangent, this is negative, this would be negative. Can you see why tangent is positive? And in quadrant 4, that would be positive, hypotenuse is positive. Can you see why cosine is positive? So mathematicians have used this idea to extend sine, cosine, and tangent beyond 90 degrees. But it's still using SOHCAHTOA in a way, because it's still using the same triangle. Now we're just basing things on reference angles, and we're adding positives and negatives. Okay, circles, circles. Questions you can circle. Circles you can question are 3, 4, 5, and 7.